So should perfect.
All right, so today we have a special talk in our Synergies series. We are very much delighted to host Dr. Laurent Fréour, who is on top of the sustainability efforts for WST, and she's presenting her wonderful research for us today. Laurent, please take it away. The floor is
Thank you,
yours.
Fatme, and thank you for the invitation on this special Earth Day.
No,
So
it's our
today
pleasure.
I would like to talk about how we can together build a sustainable future for astronomy, and in particular, how we can embed sustainability in the next ground-based facility. So I'll start with a bit of introduction. This can work, yes. So what you'll see on the screen now is what we call the climate spiral. And basically, it's the difference in average temperature, average surface temperature, with respect to pre-industrial area, which is before 1900. And you'll see like colors that are white means that it's zero difference. Blue, it means that it's a colder year, and red, it means that it's a warmer year in terms of average surface temperature. And we see that now evolving with the years. And you can see how with this type of 3D representation, we can see that in 2024, we were above +1 degrees warming in general. We were actually closer to 1.5 degrees warming, that 1 degree warming. And linked to that, so sometimes we present it like this, but yeah, to keep it very simple, we all agree it's real, it's us, and it's bad. So we are, of course, talking about global warming. It's not only about temperature warming, but more like water disruption and many other consequences in general. But I think something important to keep in mind, and especially today for Earth Day, is that there is hope. And of course, there are many things that we can do to help, and in particular as astronomers, because of course we have a very specific, a very special view of the Earth. And we know that despite there have been many exoplanets found, there is only one planet with life so far that we are sure of. So these are a bit of motivation around this talk, but now moving to motivations that are more tailored to astronomy in general. So why should we care about sustainability in astronomy? A first point is that astronomy will be impacted by climate change. There's a couple of ways. First one, it's because of average temperature warming, and there would be many instances, many days where the temperatures are in excess of the cooling system's abilities, which means that for people that are doing observational astronomy using ground-based facilities, there will be more and more pressure on getting observing time, because we might have to sometimes we might not be able to cool the telescope in an appropriate way in few days per year. Another point is that it's highly likely that there will be more extreme weather events. So this is from the IPCC report 2023, which means that we're talking about more wildfires. And I wanted to include also this picture here from a wildfire which burned Peak Mountain in 2022, and it almost destroyed the Very Long Baseline Array antenna of the NRAO. So as you know, like telescopes, they are located in remote environment, and some of them are surrounded by mountains. And wildfire can easily threaten observatories in general, but not only wildfires, we are also talking about droughts or heavy rainfall. So all these type of extreme, we don't like them. And they might be pushing a bit also the field and threatening astronomy. And I think another motivation is the European climate law. So there is a legal obligation from the EU to reduce by 2030 the greenhouse gas emissions by at least 55%, because they aim at being the first climate neutral continent in 2050, which means that we might, so far there is not a lot of regulation around new research infrastructures or research in general, but it's likely that in the near future, we might be forced into taking sustainability into consideration in the way we do science and the way we actually build new research infrastructures. So it would be good for the community in general to try to anticipate this potential obligations and try to adapt before they come. And finally, I think my favorite reason for sustainability in astronomy is really about the long timescales involved into new research infrastructures and new observatories. And we see that with the WST too. But this is just a snapshot of the ESO ELT website. And you saw that basically the green light for the design study was given in 2006. And then green light for the construction in 2014, with many milestones in between, like dome and main structure. ELT have completed in 2023, and now we are talking about first light roughly in 2029 or 2030. So we are talking about time that is 25 years, which means that people that have initiated this ELT project will most likely not be the one that are going to use it to do science. So if we want to really allow the next generation, the future generation, to do astronomy as we do, if not better than what we do now, we really need to anticipate and to try to build research infrastructures that are more sustainable, and to try to adapt also to the changing landscape and climate change in general. Now, I'd like to quickly talk about the carbon footprint of astronomical research infrastructure to give a bit of an overview and the state of the art. There was a very detailed study by Nodesder et al. In 2022, where they used what is called an economic input-output analysis. So their reasoning was to try to quantify for all the space-based telescopes, space-based mission, and ground-based telescope, to try to quantify the carbon footprint of such observatories, such missions. And to do that, they used state-of-the-art. So they tried to look at the different either space mission or ground-based observatories that had public budget, so million euros estimate of the total cost, and of carbon footprint estimate for the different phase. So for instance, if we take ground-based observatory, we are talking about a carbon footprint estimate for the construction with an associated price, and carbon footprint estimate of the operation with an associated price, and they extrapolate it to all the space mission and ground-based mission if we know their price. So then we have this type of emission factors that gives us the amount of ton of CO2 equivalent per million euro, roughly. And what they found is that for a space-based mission, 50 to 70% of the carbon footprint is coming from the launch, and the operation footprint is negligible because once the telescope is in orbit or in orbit, then it's basically not emitting anything except from data transfers, of course. And then for ground-based observatory, it was roughly half. Of course, this depends on the lifetime of facilities. The longer will the lifetime be, the more the operation footprint will dominate. But I think something that I found the most maybe striking is this number that they found, which is that basically the carbon footprint associated with astronomical research infrastructures account for roughly 36.6 tons of CO2 equivalent per year and per astronomer. If we put this into perspective, this is roughly 17 flights from Vienna, where I'm based, to New York per year. So it's quite a lot. And if we are talking about ChatGPT, for instance, it's roughly 60,000 requests to ChatGPT per day over a year. So this number is quite high. But I forgot to mention that, this is only for astronomical research infrastructure. So it doesn't take into account the traveling that we do to go to conferences or workshops. It doesn't take into account the computing either. So in this study here, we have a more complete picture of the carbon footprint of astronomers. And you can see for different research institutes in different countries how this evolved. So in the x-axis here, you have the ton of CO2 equivalent per employee and per year. And it is color scaled according to different categories of emissions. And something that is interesting is to see that observatories, so this carbon footprint that I was referring to before is not systematically included in all the studies. There is not a single way to estimate greenhouse gas emission of an observatory or a research department. That's why it can be very different depending on which study we are considering. And so another interesting point here is in Australia, the considerable, very large carbon footprint linked to computing that you can see here. It's 16 tons of CO2 equivalent per employee and per year, and this is mainly due to the high cost of energy in terms of CO2 emissions, because Australia relies a lot on fossil fuels for their energy, while France, for instance, is more based with using nuclear power. So therefore, it's way smaller. And just also to put a bit of perspective in this number, 2 tons of CO2 per person and per year is a Paris Agreement target if we would like to limit global warming to 1.5 degrees, but this target is now out of reach, so we are more talking about a 2 degrees warming by the end of the century anyway. But this is the target, so there is a lot of work to do in astronomy to try to bring this curve all the way below this 2 tons of CO2 equivalent per person per year. Okay, so this was a lot of observations, a bit maybe worrying in a sense, but I think there is a very good news that is worth being highlighted here, and it's very also relevant for the WST. The first one is that, so overall, we see a change, we see a system shift in how academia is going to work in the next years. There is the ESO Expanding Horizon call, under which the WST will apply, to which the WST will apply, and they have published 5 criteria to choose the next facility. And sustainability is officially listed as one of these criteria. So this was a very good also way to try to push for sustainability, to embed sustainability directly in the design of new research infrastructure. And then if you're a early career researcher, you might be, or a researcher in general, you might be also applying for funding. And something that is visible now is that the funding agencies are starting to encourage sustainable practices within the proposals. So we see that with Marie Curie Green Charter, which I think got introduced a couple of years ago, where we had to write now like a full paragraph on how our project would impact the environment. Here's the FWF, it's a national Austrian funding agency for science. And indeed, also since 2025, last year, we have to fill now a statement on environmental sustainability in the research proposal of some specific programs. So we see that there is really this shift toward a more sustainable way of doing science and of planning projects in general. Okay, so now I would like to talk about what we do at the WST, and I will present the work package 6.4 of the WST consortium, which is dedicated to sustainability. So the goal is to include sustainability consideration in the design phase of the WST. We are 22 members in Slack right now, and as part of this work package, there was a 1-year postdoc position opened and fully funded through the Horizon Europe grant. So I'm working with this position right now, and I started in April last year, and my contract, because I'm part-time, will end at the end of June. So what we have done and what we are going to do. So first, what we have done, the first thing was to include the carbon footprint as a trade-off parameter in the integral field unit design study. And I'm going to present this just after. And some ongoing work also. We are currently doing the same with the multi-object spectrograph study. And we are also trying to assess the environmental impact of the large volume of data expected. And this is probably directly relevant to time domain astrophysics, because I guess you're familiar that it requires so much data. But then what do we do with this data? We need to process it, then we need to store it. So these are considerations. that we're currently talking about in order to try to minimize the environmental impact of the data. Okay, so moving to the completed work, the carbon footprint as a trade-off parameter in the integral field unit study. So this work was done in collaboration with Roland Bacon, Corentin Kidenek, Etienne Burtin, and Bodo Ziegler, and the goal was to compute the carbon footprint associated with the construction and one-year operation of the several spectrograph designs and cooling systems. So in practice, what does it mean? We had roughly 13 spectrograph optical designs that were different in terms of what type of glass we are using for the lenses, for instance, the weight of the different spectrograph, and also the total number of spectrographs. So we had variation between 128 spectrograph for the IAFU to 192 spectrograph for the integral field unit. And on top of that, we also explored different type of detectors and cooling system. The first one was using CCD with cryocooler linear pulse tube. And the second type was using CMOS with a combination of thermoelectric cooler, Peltier type, and CO2 cooling system, liquid CO2 loop. So in total, this gives us 26 different possibilities for the design of the IFU. And my goal in this study was to use what we call a life cycle assessment to assess the environmental impact of each type of possibility. So now, life cycle assessment, what is this? It's a method that is used to quantify the carbon footprint, the environmental impact from the very beginning, so raw resource extraction, going through the processing of these resources, the manufacturing of the resources, you can see it here, the distribution, so transport, and finally the use phase of the product, which in our case would be the operation phase of the integral field unit. And finally, the end of life, which we don't integrate here because it requires a lot more considerations with waste management, recycling, and many other things that are a bit complicated. So going back to this construction versus operation of instrument, and in this case of the different design for the integral field unit. So what you can see here is different design type gathered in three main categories. Category 1 with the highest number of spectrograph, 192 spectrograph, category 2 with 144 spectrograph, and finally category 3 with 128 spectrograph. In general, the design with more spectrograph also have a lighter spectrograph than the design with fewer spectrographs that tends to be more heavy. And I think it was quite interesting to see that how the percentage of carbon footprint linked to operation is put into perspective with the one for construction. And these are results that are aggregated over 20 years, which means that, yeah, roughly, I mean, after 20 years, and especially if we are talking about the 50 years lifetime of the WST, construction will be quite small, negligible with respect to operation footprint. And you can see it here. For instance, for this 128 spectrograph, operations account for roughly 85% of the total footprint for 20 years. So it's going to be even more for over 50 years. Now about the operation part, I also computed the mean carbon footprint for 1 year of operation. That's what you can see here in terms of ton of CO2 equivalent. So we find again the three main categories here with 192 spectrograph, 144 spectrograph in this pale yellow, and 128 spectrograph in this pale green. And we see the different type of detectors and cooling system. So the plots with thick dashed black line correspond to the CMOS detectors, here, here, and here. And the other one are with CCD detectors. So overall, CMOS, they can work at higher temperatures, so they don't need to be cooled they need to be cooled, of course, but they need to be cooled to a higher temperature than CCD. So they will overall consume less energy in terms of cooling system than CCDs. So that's why you see that systematically for the same number of spectrograph, we have CMOS options that are quite lower in terms of carbon footprint with respect to CCD's option. And another important aspect is that, of course, designs with a higher number of spectrographs, this means that you have more detectors. So there are 2 detectors per spectrograph. So in the case of 192 spectrograph, we have 384 detectors that needs to be cooled every day, 24 hours per day to very low temperature. So we are talking about, I think, 150 Kelvin for CCDs and 190 Kelvins for CMOS. So it's going to draw a lot of energy. Therefore, it's going to have a higher impact. So the more detectors and spectrograph you have, the higher in general for the same CCD or CMOS option, the impact is. And then, so these numbers, they were included in what we call the trade-off parameters matrix. So basically, the idea is to give a score for different parameters. So we have here image quality, throughput, spectral properties, size, cost, and risks, accessibility, and finally, environmental impact. That accounts for 10% of the weight for the parameters. And you rank for each parameter, you give a grade for each design option, the best one versus the worst one. And then we have a complete overview to classify the design from the best one, the most favorable one, given all these parameters, to the worst one. And that's how we included the environmental impact using this carbon footprint estimate into the trade-off parameters to select the design for the integral field unit. Okay. So now moving on to ongoing work, I'd like to mention the impact of data, as we are currently actively working on this topic. So it's done in collaboration with Arlette Lecontal, Peter Velbacher, and the WST Project Office. So as I said, we are talking about quite a lot of detectors. So I mentioned 384 roughly for the IFU, but it's going to be more because we also have the multi-object spectrograph. And we are talking in total about roughly 650 detectors. So as a first approximation, the volume of data roughly scales with the number of pixels, which roughly scales with the number of detectors. So more detectors means more data. And right now, the first estimate are that we might generate 1.7 petabyte of raw data per year. And this raw data means, so the more data we have, the longer the reduction pipelines will run to reduce this data that you then as scientists will be able to use. And this means that if the reduction pipelines run more, of course, we need more energy to power the hardware. And more storage space, we also need to store this data. And this is screenshot that I took from the green algorithm. I didn't put the link, I should do that. From the green algorithm computation, which is basically a software or an interface that you can use to compute the carbon footprint associated with your code, or in that case, with the reduction pipeline of the IFS. And basically, we estimated using this code that the carbon footprint to reduce one full night of data just coming from the IFS would be 106 kilograms of CO2 equivalent per night, which is basically the equivalent of flying from Paris to Dublin every night to reduce the data. So it's quite a lot. Of course, this was based with processing data center being based in Germany, in Gorking, as it is done now for ESO. But if we change this and we move the place where we run this algorithm to France, for instance, where the carbon footprint of energy is quite low, this carbon footprint is divided by a factor roughly 10. And on this, I just wanted to also show this map, which is quite interesting because it shows you the countries with lower or higher carbon intensity with respect to the energy. And so green means that the country is very green in terms of energy, so it has a carbon intensity that is very low, while red means that the countries have a carbon intensity that is very high. I mentioned France just before, so you can see it's here, it's roughly 44 grams of CO2 equivalent per kilowatt hour. Germany is rather very high. It's, I mean, it's on the high side. I think it's roughly 230 gram of CO2 equivalent per kilo water. So that's why you have difference also on where it's important to understand and to come to discuss where we will store the data and where we will process the data, because this can have very big versus very low impact depending on the location of the data centers for the WST. So it's currently work in progress. And yes, now moving to my conclusion. So sustainability should be integrated as early as possible in the design of new research infrastructures, and that's really what we try to do here at the WST, already including it in the design phase, because that's when we can really mitigate it efficiently and anticipate it. So like cost, scientific performance, and risk, it can be integrated as a trade-off parameter to select the best design for instruments. But this can only be done in collaboration among engineers, the project offices, and scientists. And that's also what we try to do to make possible in the WST through this work package 6.4 on sustainability. And also wanted to just put a beautiful picture of the Earth, of things that we can see on Earth, because I was hesitating with Artemis 2 picture of Earth seen from the moon, but I thought actually we don't need to go that far to actually witness how beautiful the Earth is. And on this, thank you for your listening. If you have any question, I'm happy to take them.
Thanks so much. This was a wonderful talk. Okay, so questions, comments from the audience? So I think I will start from somewhere myself. I have a question. So you have some calculations about the IFS data reduction. I was wondering if you have done the same for MOS, because maybe you have different modes, observation modes for WC. And how do they compare? Because I think like the IFS would be the most data extensive mode of detection, right? So like everything else should be much lower, my assumption.
Yes, very good assumption, indeed. So we don't have very good estimate for the most, because basically so far we are still at a very early stage on all this data processing discussion, but it would be from the first estimate at least 1,000 order of magnitude lower in terms of impact, because the processing time for the data is much lower, of course. So
Right.
it should
But
be
accumulated across years, I suppose it's going to be very significant, right? Even on the MOS mode.
yes, but it's still going to be the IFU that will dominate
Right.
in terms of data processing. So I think we might, as a first estimate, just neglect it and then maybe include it later.
And the data reduction pipeline assumptions that you're taking into account, I suppose, are coming from the reduction pipelines we already have for Muse, for example, or like other facilities. So,
Exactly.
right? Okay.
Yes, it's from use. So this, yeah, what I just showed here is probably higher limit. I mean, we hope it's a higher limit, because it's in the case of Muse data that where the pipeline was designed, I think maybe 20 years ago. So maybe now we hope that we can have something that is more efficient, so that we can reduce the energy needed and the runtime of the computations.
Right. Do you know what is the base language of this pipeline?
That's a
Is
good
it
question.
ideal C or
I
different?
don't know.
Okay.
Yeah, I can ask if you're interested.
No, I can also like have a look. No worries. Yeah, I just thought like if it is like on top of your mind. Hmm. Okay, very interesting. Yeah. Is it going to be published soon? Because I haven't seen it on archive, or is there like a draft on archive already?
Yes, so there is no draft already. We are working on an article for the SPIE conference where we'll present the sustainability work. So it should be normally published before mid-June.
All right. Absolutely, yes.
Yes.
Okay, perfect. Any other questions? Okay. Thank you. If not, we thank Laurane again. Thanks so much for accepting our invitation. This is a great talk.
My pleasure.
And
Thank
you so
you.
much.
Thank you everyone for joining, and thank
Have a
you
nice day.
for
Bye-bye.
organizing.
Thank you.